is about an 80, which is average, normal for an exam grade. And so I think that that's a-okay. If you did well, congratulations. If you didn't do so hot, better luck today, and I hope that this material is maybe sitting a little bit better with you. Before I jump into chapter 14 here, do you have any questions that I can answer for you? All right. Hearing none, seeing none in the chat, I'm going to keep going here, and we're going to get started with chapter 14 stuff. So chapter 14, all about equilibrium. In order for us to talk about equilibrium, we have to remember chapter 13 stuff. And from chapter 13, if we have a reaction A going to B, then we know that, let me get a pen here. We know that the rate is equal to negative change in the concentration of A over change in time, which is also equal to the change in the concentration of B over the change in time. When we're at equilibrium, then the rate of the forward reaction has to be equal to the rate of the reverse reaction. So the rate of the forward reaction right? That is A going to B equals the rate of the reverse reaction which would be B going to A. And when we start writing equilibrium, we're going to start writing these double arrows, right? And so if it's in equilibrium, not only does it have a forward arrow, but it also has a back arrow. One thing I want to point out, we don't put a double-headed arrow because if you remember from chapter 9, in Lewis structures, that double-headed arrow implies that it's a resonance, and these are not resonant, these are in equilibrium. So there's a slight difference, but we need to be careful about that. All right. So what does equilibrium mean for us, right? Equilibrium in a chemical sense, well, let's back up. Equilibrium in a non-chemical sense, right? Thinking about balancing on a balance beam or on a tightrope, right? If you're in equilibrium, then you're not tilting right, you're not tilting left, you're staying right on that tightrope. Chemical equilibrium is a similar concept. There's no change that we can tell as time goes on, right? And so our chemical definition for equilibrium, this is a state where there are no observable changes as time goes. So as time continues, we get to a point, we get to this equilibrium where we can't tell that anything's happening in our reaction. And so what we think about when we think about chemical equilibrium in particular, right? These two data points here, these two bullet points, as I mentioned on the first slide, the rate of the forward reaction equals the rate of the reverse reaction. And this is important, right? We spent all of chapter 13 talking about reaction rates, and now I'm saying that the reaction of A going to B happens just as quickly as the reaction of B going to A. And so these two reactions happen with exactly the same rate. And so that doesn't mean that it has stopped reacting. It just means that for every 5 molecules of A that turn into B, there are 5 molecules of B somewhere that turn into A at the same time. Right? And so the reaction is still happening. The reaction is still occurring. It just has reached this equilibrium where, you know, there's nothing changing that we can see. Think about, you know, filling a bucket with water. For the first minute or two, you're actually filling that bucket with water, and you can see the volume of that bucket changing. But there comes a point when that bucket's full and it starts overflowing, that the volume in the bucket isn't changing, but the water going in, the water going out is different water, right? It's not that I've moved my spigot over and the water in the bucket just all stays the same, right? It's that I'm adding new water and different water is leaving. And so this is the idea of chemical equilibrium. And this is sort of a way of thinking about the fact that the concentrations of the reactants and the products stays constant once we reach equilibrium. And so, you know, we before that bucket is full, while this reaction is still changing and we can see the change, we're not at equilibrium, right? That bucket's not full yet. The volume in that bucket is changing. The concentration of our reactants and products are changing. But once we reach equilibrium, once that bucket is full, then the reaction still happens. The volume in that bucket stays constant, but the water going in and the water going out is different. And so if we look at some examples of equilibrium here, we can have it either in a physical sense, so states of matter, or we can have it in a chemical sense. And so we could have this equilibrium between solid water and liquid water. And we mentioned this a little bit in chapter 12 when we talked about phase changes. Right? We talked about the fact that while that phase is changing, while we were on that horizontal line in our heating curve, or while we were on one of the drawn lines in our phase diagram, that's actually an equilibrium between phases, an equilibrium between solid and gas, or solid and liquid, or liquid and gas. And what that means is that on that line, as much solid is becoming liquid as liquid is becoming solid. Now that's a physical change, right? There's not a chemical event happening there. We can also have a chemical change. If we look at this example with NO2, 2 molecules of NO2 stay in equilibrium with 1 molecule of N2O4. These are both in the gas phase. And this one is very pressure dependent, right? You increase the pressure and we get N2O4. You decrease the pressure, we get NO2. We'll talk about why that is a bit later today. So another way that we look at equilibrium, I've told you a lot, scientists like graphs, right? And so one of the ways that we look at equilibrium, in this example, if we start with just NO2, here we have a lot of NO2 at the beginning and we have 0 N2O4, and they react for a while, and over time we reach equilibrium, right? And so this line right here is the time at which we reach equilibrium. Now, we will reach equilibrium even if we start with just N2O4 rather than starting with NO2. Here we have only N2O4 and we have no NO2. we still reach that equilibrium. I'm just going to abbreviate it EQ. That equilibrium looks a little bit different. Those concentrations are not identical, but they're related to our initial concentrations. And so we could start with a mixture of these two. We could start with a little bit of NO2 and a little bit of N2O4. And again, we'll reach another equilibrium. And so all of these vertical lines here represent equilibrium. And you'll notice that after that point in time, the concentration of the products and the reactants doesn't change, just like we mentioned earlier. Any questions about equilibrium so far? All right. So that being said, like I said, we're going to take these graphs, we're going to try to interpret them a little bit. So we run lots of different experiments, right? So some scientist somewhere at some point ran a lot of these experiments, and he said, okay, I'm going to start with no NO2 and a little bit of N2O4. They reach an equilibrium, and let's try it again, right? I'm going to start with a little bit of NO2 and a little bit of N2O4. They reach equilibrium too, but those concentrations are different. All the way down to starting with just NO2 and no N2O4, we still reach an equilibrium, and yet they're all different values. Right? And so the concentrations are all different. And so when we reach an equilibrium, it's not about reaching some magic concentration. What we do is we play around with those numbers, we play around with those ratios. And if we just took the ratio of, products over reactants, then we get these numbers, and these numbers are not constant. These numbers change a whole heck of a lot. Right? But if you remember our reaction, N2O4 in equilibrium with 2 NO2. If I take that 2 and I turn it into an exponent, all of a sudden, those ratios start lining up beautifully. If you look at these, this whole column here, these are pretty constant. Yes, it's true they vary a little bit in the third significant figure, but generally speaking, this is a pretty constant value. And it turns out that the way that we talk about equilibrium and what's constant about equilibrium is related to this ratio of concentrations raised to the exponent of the coefficient. So let's dig into that a little bit more. Again, we're going to look at the same reaction. N2O4 going to 2NO2. In chapter 13, we talked about little k, and little k was the rate constant. In chapter 14, we're going to talk about big K, and big K is the equilibrium constant. Okay? And so big K is equal to, we saw on the last slide, the concentration of NO2 squared over the concentration of N2O4. And this is a constant value. We saw again from the previous slide that this was about 4.63 times 10 to the negative 3. And K is unitless, right? Big K is unitless. Because the way that we sort of standardize concentrations, we drop the unit from our equilibrium constant. And so if we have a more generic reaction, not just N2O4 going to 2NO2, but if we had A moles of A and B moles of B in equilibrium with double arrow, C moles of C and D moles of D, well, which is going to go on top, A and B or C and D? And how do we know?
C and D.
C and D because why?
I just took a guess. Products over reactant.
Yeah, so if we take a look at the one that worked for our experiment, this is a product on top. And so we're going to do exactly that, C and D on top. So a K is C and D. Now, we took this coefficient and we used it as an exponent. And so I'm going to do little c as an exponent and little d as an exponent. In the denominator, I'm going to have concentration of A to the A and the concentration of B to the B. And this is our equilibrium constant. And this is the form of that equilibrium constant for every reaction out there. A couple of things I want to point out while we're talking about this. In looking at rate laws, for the overall rate law, we did not pay any attention to those coefficients. So we had to determine the rate experimentally using a table of data. But for the elementary steps in the rate mechanism, that quest is coming up in 35 minutes. For the elementary steps in a rate mechanism, reaction mechanism, the coefficients were the orders for those elementary steps, right? Same is true here for the equilibrium constant. The value of the exponent is equal to the value of the coefficient. Okay? Now, one quick thing here, because these are in terms of concentration, you will sometimes see a little c, k sub c. That's because it's in terms of concentration. Right? So that's the equilibrium constant for concentration. All right, and so let's talk a little bit about what K really tells us. And so if K is much greater than 1, that means our numerator is large and our denominator is small. Since products is in the numerator, reactants in the denominator, that means we have lots of product and a little bit of reactant. And so K greater than 1, we end up favoring products. And so if K is greater than 1, the reaction favors the product. And we can talk about this a couple of ways. Sometimes we say, towards the products. Another way we say is that the equilibrium lies to the left. Sorry, to the right. Right? The equilibrium shifts towards the products, and so equilibrium lies to the right. If the opposite's true, K is much less than 1, that means little products, lots of reactants. And so K less than 1, we're going to favor reactants. And we're going to say that the equilibrium lies to the left. All right. So there's two ways for us to sort of approach writing an equilibrium constant, writing this equilibrium ratio. The first is for what we call homogeneous equilibrium. In this case, all reactants and products are in the same phase. It could be gas phase, like this example. It could be that they're all dissolved in water, so they're all aqueous. That's a very common one. It could be that they're all solids, and we have some kind of odd solid reaction going on. But in any case, it's a homogeneous equilibrium because they're all in the same phase. Oops. And so, again, we know how to write our Kc for this guy. We end up with the concentration of NO2. Oops, squared. We don't need that squared. over the concentration of N2O4. But when we talk about gases, concentration is kind of a weird thing to talk about, moles per liter for a gas. You can do it, and it's absolutely okay. But when we talk about gases, we're more likely to talk about the pressure of a gas or the partial pressure of a gas in a mixture. And so we can write, remember I told you this is Kc for concentration, we can write a Kp for pressure, and that's just the pressure of NO2. I'm going to signify that by capital P for pressure, NO2 down here as our subscript. And just like the concentration gets squared, the pressure gets squared. And on the bottom, the pressure of N2O4. Now, pressure and volume, pressure and concentration are related to one another. Just as a quick aside here, PV equals nRT. If we want concentration by itself, that's N over V. If we rearrange, N over V gives us P over RT. And if we go one step further, pressure is equal to this concentration. This is concentration. I'm just going to use A as a placeholder here, times RT. And so the concentration and the pressure are related to each other by this factor of RT. And so if we square the concentrations, we're going to square the pressures as well. And so we have it in terms of concentration. We have it in terms of pressure. Now, of course, we're not going to use the Kp if it's all solids. We're not going to use Kp if it's all aqueous. We're only going to use this if it's gases. Now, because pressure and concentration are related to one another by the ideal gas law, there's a relationship between Kc and Kp. And so if you know one, you can figure out the other. And so Kp is equal to Kc times RT. That looks real familiar, right? We have pressure, we have concentration, we have that factor of RT. But I'm missing one piece. That RT is raised to the power of delta N, change in the number of moles, right? And so, again, let me change my ink. This is the change in the number of moles of gas. And so moles of gas products minus moles of gas reactants. And so for N2O4, we can do this math. Right? We know R, we know T, we know Kc from the table. And so let's do this real quick for N2O4 for this reaction. Kp is equal to 4.63 times 10 to the negative 3, oops, times 10 to the negative 3. Right. R, which R are we going to use? 0.0821 liters atmospheres mole Kelvin, or 8.314 joules per mole Kelvin? We're dealing with gases here, so do we need the liter atmosphere or do we need the joules?
Liter atmosphere.
That's right. So we have 0.00821 liter atmosphere per mole Kelvin times, now that table told us that it was at 25 degrees C. We need that in Kelvin, so that's 298 Kelvin. And now we need to calculate delta N. For this reaction, we have 2 moles of gas on the right and 1 mole of gas on the left. 2 minus 1 is 1. And so even though we normally don't write exponents of 1, I'm going to just put it in there. And so we can do this, Kp 4.63 times 10 to the negative third times 0.0821 times 298. And so Kp 0.113. So as long as we know the reaction and we can calculate the number of moles of products minus the number of moles of reactants in the gas phase, and we have to know temperature because since rate depends on temperature, equilibrium constant is also going to depend on temperature. So we have to know the temperature in order to know the equilibrium constant. As long as we know those things, we can find Kp as long as we're given Kc, or vice versa, right? If we're given Kp, we can find Kc. All right, one more thing. Here, everything is in the liquid phase, right? This is another homogeneous equilibrium. Everything's a liquid. However, we have this little caveat here. This is aqueous, this is aqueous, this is aqueous. Water is not aqueous. Water is not dissolved in himself, right? That's a weird thing to think about. The other thing is that the concentration of water isn't really changing as long as everything's dissolved in water. If you have a liter of water with only 1 mole of solute, well, you still have 55 moles of water in that liter. And so there's a lot of water and that concentration is not changing a whole lot. The change is negligible, we say. And so because of that, well, if we looked at Kc, Kc would be equal to, again, products over reactants, CH3COO minus H3O plus divided by CH3COOH times H2O. But however, since this H2O is a constant, right? Again, it's not truly constant. It's changing a tiny, tiny bit. Because there's so much water in our solution, the concentration change is negligible. And so we say that the concentration of water is a constant. Since that's true, we can bring it over with our other constant, Kc. And so Kc times the concentration of water, we give this a new symbol, and we give it, and we talk about it as, we talk about this as Kc prime. That includes everything. And then this is equal to our Kc, which is only the things that change in concentration, CH3COO minus times H3O plus divided by CH3COOH, and we don't worry about the concentration of water. Right? And so we do not include not only water, but any pure liquid or solid. In our Kc expression. Okay. So if it has a liquid or if it is a solid, we ignore those, we leave those out when we write our equilibrium constant. Okay. And so the equilibrium constant for the reaction is just that. All right, so let's take a few minutes and do some practice problems, right? You have these in front of you, hopefully. I'm going to give you a few minutes to work on these next 4. They're all right next to each other. Example 1, 2, 3, and 4. take, I don't know, 10 minutes and just work on these. And then we'll come back. Maybe it won't take 10 minutes, but we'll come back and we'll see how you're doing um, with these equilibrium constants.
Hey, Dr. Davis, is there any way we can go back? It's moving the screen really quickly.
Sure. How do we feel about those ratios? Products over reactants raised to the power of the coefficient for that particular compound. And again, we're going to ignore pure liquids and pure solids. For the second one, it gives you all the equilibrium concentrations and it asks you to find Kc. Now this is important. It tells you that these are the concentrations at equilibrium, right? If it told you that these were initial concentrations, for example, there's no way for you to find Kc. The concentrations have to be at equilibrium in order for you to calculate Kc. Again, this is one of the ones from the previous slide, and so we knew what Kc was. Products of reactants raised to the power of the coefficient. We just had to plug in all of those values and do a little math. Remember too, the convention is that we drop the concentration unit from our numbers as we plug those in, and so our Kc is unitless. One way for us to check and make sure that our number might be kind of right, especially in a reaction like this, is using that information about the fact that if Kc is greater than 1, it's going to favor the products, and if Kc is less than 1, it's going to favor the reactants. We have a huge concentration of our product relative to our reactants, and so our Kc value should be large. Right? NO2 is our product. It has the highest concentration by a lot, and our Kc value is very large because of it. And so that's a good way to just make sure you haven't switched some concentrations or something like that. For the third one, they give you Kp, and I ask you to solve for one of the pressures. Remember, Kp is set up just like Kc, except in terms of pressure instead of concentration. And so it's just the pressures of the products divided by the pressure of the reactants, raised to the power of the coefficients. In this case, they were all 1. Raised to the power of the coefficient, we just plug through and solve. All right, and then this last one, we know Kc and we're asked to find Kp. So liter atmospheres per mole Kelvin times our temperature, that's going to be 493 Kelvin. And I need to raise this to delta N. With delta N here, I have 1 mole of gas in my product, and I have 3 moles of gas in my reactants. So delta N is -2. So I need to raise this to the power of -2. So if you're playing on a calculator like this, you have a button, or you have a button similar, that looks something like this. It's X to the Y. I'll write it on the screen, maybe that's easier. If you have a button that's X to the Y, let me get my other calculator. If you have the TI version, it's a little bit easier maybe. If you have the TI version, you just have the caret button, right? And so either way will work. But to plug it in, you just multiply those two numbers together. So 0.0821 times 493. So that's 40.475. And so in your calculator, you can either do the x to the y button, -2, or you can do 40.475 in the caret button, -2. Both of those will work for your negative exponents. So 40.475 to the -2 times 10.5. And we end up with a KP of 6.41 times 10 to the -3. All right, so for those 4 problems, any questions? Any concerns? All right. Well, the last thing we're going to end with today is we talked about homogeneous equilibrium. Now we're going to talk about heterogeneous equilibrium. And so this is the case where all of our states are not the same, right? All of our phases are not all the same. And so heterogeneous equilibrium is when reactants and products are in mixed phases. Maybe that's not the best word, mixed. I'll just say different phases. I don't want you to think when I say different phases that the reactants have to be one and the products have to be something different. It can be, like in this example, the products are both a solid and a gas. Now, it works exactly the same way as it did for homogeneous equilibrium, with that exception, that caveat that I gave you about leaving out pure solids and pure liquids. And so, well, we have a pure solid here and a pure solid here. And so our Kc is just equal to the concentration of CO2. And our Kp is just equal to the pressure of CO2. So
Dr.
these,
Dave,
yes.
this may be a dumb question, but how do you know if it's a pure solid, just if it's a solid?
Yeah, exactly. So just if it says solid in parentheses, we're going to treat it like it's pure. And so the reason we ignore those is because, again, the concentration of that solid it isn't changing over time. If I have a little bit of pure salt and you take some away, well, the concentration of what I have left is still the same concentration. And so we do not include concentrations of pure solids in liquids. Okay. All right. Last slide for today then, the same reaction, just sort of demonstrating why we don't really care a whole lot. If I have a whole lot of this calcium carbonate, that's going to be our yellow compound. Maybe it's orange, I don't know, somewhere in there. And the CaO is our green. So if I have a ratio where it's a lot of calcium carbonate and a little bit of calcium oxide versus the opposite, a lot of calcium oxide and a little bit of calcium carbonate, when things reach equilibrium, if we notice, again, this is a manometer, and maybe you saw it in chapter 5, maybe you didn't. I did not say a whole lot about it, but what it does is it uses the height of mercury, or any liquid really, to demonstrate the pressure within a container. And so if we look at these two, the height of them is identical, right? So it's the same pressure of CO2, no matter how much of our solid. And I think I wrote over what I'm going to say here. Yeah. And so the pressure of this CO2 does not depend on either of these solids. And so that's why we don't include them when we talk about our equilibrium constants. Okay, well, that's 10:20. We will start back on Monday, maybe in person, maybe not. We'll see. We'll start back on Monday doing a couple more examples with KC and KP, and then we'll talk some more about using equilibrium constants and more about chemical equilibrium. Have a good weekend. Shoot me an email if you have any questions, or you can hang on here and I'll answer any questions after class.
Thanks, Dr. Davis.
Thank you.
Have a good weekend.